Welcome back, everybody. This is our third session in JEE Mains previous year questions for chapter Nuclei of class 12th. Before this video, there are two videos available on our playlist regarding this chapter. And if you find these videos useful, then do press the like button, share them, subscribe to our channel. Also like to support us financially, scan the QR codes in front of your screen and donate us any amount you want. Any amount will be highly appreciated. With this, let's start today's video. In the previous one, this was the last question which we covered, and today we will start with question number 28. So activities of three radioactive substances A, B, C are represented by the curves in the figure. Their half-life are in the ratio. So we have to find out the ratio of their half-life. Now, regarding activity, we have relation that R is basically equal to R node e raised to power minus of lambda t. Now we can see that here graph is between ln R and t. So let us take log. So we will get ln of R is equal to ln of R node minus time lambda t. So basically this will be a constant term. So this is basically y is equal to c plus mx. This is the type of equation where we have, and here slope, that is m basically, that will be equal to minus of lambda, because this ln r is acting as y, time is acting as x, so slope will be here minus lambda. And we know that lambda is basically ln 2 by t half. So let's calculate for A. Now for A, we will take 2 points. This point will be 0, 6 and this point will be 10, 0. So lambda for A, that will be equal to delta y by delta x. Let us take 0, 0. So change in y, that will be equal to, that will be 0 minus 6. We are taking this point first, and change in x will be 10 minus 0. So that will be basically minus 6 by 10. Now using this relation, that slope will be equal to minus lambda. Oh, sorry, this is slope. M is 0 minus 6 by 10 minus 0. So slope is minus 6 by 10. So from this, lambda will be equal to negative of the slope, that will be 6 by 10. Now using this relation, so we can write that 6 by 10 is equal to ln of 2 divided by ta half. And from this we will get the value of ta. So ta half, that comes out to be 5 by 3 ln of 2. Now let us do similar calculation for B. For B, slope will be this point will be 5, 0. So slope will be 0 minus 6 divided by 5 minus 0. So that is basically minus 6 by 5. So lambda will be negative of the slope, so that will be 6 by 5. And for B again, we can use this relation, that 6 by 5 will be equal to ln 2 divided by t of B, that is basically half time. So half time for B will be equal to 5 ln 2 by 6. Similarly for C, here for C, this is the point, that will be 0, 2. So for C, I can write that slope will be equal to 0 minus 2 divided by 5 minus 0, that is negative 2 by 5, and lambda will be negative of the slope, so 2 by 5, and that will be equal to ln 2 by t half time for C. And so from this, half time for C is 5 by 2 ln of 2. Now their ratio. So for A it was 5 by 3 ln 2. So for A it was 5 by 3 ln of 2 ratio 5 by 6 ln of 2 ratio 5 by 2 ln of 2. So ln 2 and 5 gets cancelled, and we are left with 1 by 3 ratio 1 by 6 ratio 1 by 2. Let us multiply each also side by 6. So what we will get? We will get 2 ratio 1 ratio 3. So that is option C for us. So option C is the right answer here. Let us move to the next one. A radioactive nuclei decay into two different processes. Half of the first one is 10 and that of the second is 100. Second, the effective half-life. So in these type of scenarios, the effective half-life is given by that 1 by T effective will be equal to 1 by T half for the first plus 1 by T half of the second. This is for first and this is for second. And also we have the relation that lambda combined, if you want to find out lambda combined, then that will be equal to lambda 1 plus lambda 2. And we know that basically lambda is ln 2 by T half. So we can derive this expression from this one. So let's substitute the values. That will be 1 by 10 plus 1 by 100. So that will be basically 11 by 100, and T effective will be equal to 100 by 11. So that will be approximately 9 seconds. So option A is the right answer here. Now in the next one, in a radioactive material, fraction of active materials remaining after time t is 9 by 16. Fraction what was remaining after t by 2. So we know that for Nt in a radioactive substance, Nt is equal to n node e raised to power minus lambda t. Here Nt is the amount of substance remaining and n node is original amount. So I can write it like this, that Nt by n node, this will be the fraction of remaining substance, is equal to e minus lambda, e raised to power minus lambda t, and it is given to be equals to 9 by 16. So 9 by 16 is e raised to power minus lambda t. So now let us write the same equation for time t by 2. So what we will have, n t by 2 will be equal to n node e raised to power minus lambda into t by 2. So from this, n t by 2 divided by n node, this is the fraction remaining after time t by 2, will be equal to e raised to power minus lambda t by 2. So suppose this is x. Suppose this fraction is x, so I can write that x is equal to e raised to power minus lambda t by 2. Now if I take ln, so ln of x will be equal to minus of lambda t by 2. Now similarly here, if I take ln, I will get ln of 9 minus ln of 16 is equal to minus of lambda t. Now I can substitute this value here. So what I will get? I will get ln x is equal to ln 9 minus ln 16 divided by 2. Now I can rearrange it slightly, that I can write it like this. Twice of ln x is equal to ln 9 minus ln 16. Now I can rearrange it further like this, that ln of x square is equal to ln of 9 by 16. And from this we can cancel ln from the both sides. So x square is basically 9 by 16, and from this x comes out to be 3 by 4. That is option C for us. Now to the next question. The activity of a radioactive sample falls from 700 per second to 500 per second in 30 minutes. The half-life is close to. So for activity, we have already have relation that R is equal to R naught e raised to power minus lambda times t. So after some time, that activity is come 500 and we started with 700, and that comes to e raised to power minus lambda t, where t is 30 minutes, and we have to convert. Oh yeah, answer is options are also in minutes, so we don't need to convert it in seconds. So from this, I can write that 5 by 7 is equal to e raised to power minus of 30 lambda. Now let us take log. So ln 5 minus ln 7 is equal to minus 30 lambda. And from this, if I solve, I will get lambda is equal to 0.336 by 30. So that will give us 0.0112. That is the value of lambda. Now from this I can calculate t half. So t half will be equal to ln 2 divided by lambda, that will be 0.693 divided by 0.0112, and that will be equal to 61.87 minutes. So basically 62 minutes. That is option B for us. Now let us move to the next one. Two radioactive material A and B have decay constants 10 lambda and lambda respectively. If initially they are in the same number of nuclei, then the ratio of number of nuclei for A to B after time 1 by E will be equal to. So for both of these, we can write basic radioactive equation that AT, amount of A remaining after some time t, is equal to A node e raised to power minus lambda AT, and similarly Bt will be equal to B node e raised to power minus lambda Bt. So this becomes A node e raised to power, for A it is 10 lambda, so minus 10 lambda t, and for B it is basically lambda, so B node e raised to power minus lambda t. Now it is mentioned that time is 1 by E. So A at 1 by E, so that will be A node e raised to power minus 10 lambda by E, and that will be Bt will be equal to B1 by E will be equal to B node e raised to power minus lambda by E. Oh, sorry, I made a mistake. I misinterpreted the statement. It is asked that we have to calculate the time after which they become, their ratio becomes 1 by E. So this is wrong here. What I have to do, I have to just divide both of these. So AT by BT, I have to calculate the ratio, is equal to A node e raised to power minus 10 lambda t divided by B node e raised to power minus lambda t. Now, initially mentioned, they have same number of nuclei. Initially, they have the same number of nuclei. So A node is equal to B node, and this ratio is 1 by E as defined. So this becomes e raised to power minus 10 lambda t plus lambda t. So that is minus 9 lambda t. Minus 9 lambda t. Now let us take logarithm. So that will be ln 0 minus ln of E, that is minus 9 lambda t. This will be 0, this will be 1. So 1 is equal to 9 lambda t, and from this time is 1 by 9 lambda. So option A is the right answer here. In the next one, two radioactive substances A and B decay constant 5 lambda and lambda respectively at T is equal to 0. The sample have the same number of nuclei. Time taken for the ratio of nuclei to become 1 by E square. So it is similar to the previous one. Here we had 1 by E, and now in this next one we have 1 by E square. So using the same equation, I can write that AT by BT will be equal to A node e raised to power decay constant for A, that is 5 lambda, so minus 5 lambda t, and for B it will be B node e raised to power minus lambda t. So A node, B node are equal, they get cancelled. This ratio is 1 by E square. So this will be e raised to power minus 4 lambda t. Now if I take ln, so I will get ln 1 minus twice of ln E is equal to minus 4 lambda t. So minus 2 is equal to minus 4 lambda t, and this from this time is 1 by 2 lambda. That is option A. Now let us move to the next one. In a radioactive decay chain, initial nucleus is 232 thorium, and at the end there are 6 alpha 4 beta particles which are emitted. So we have to find out the end nucleus. So we have 232 thorium and 90, and it gives rise to 6 alpha, means 6 times 4 He2 plus 4 beta particles, and these are basically beta particles are basically electron. So what we have 40E. Atomic number for electron is actually already 0, sorry, mass number, but we will take -1 here because we have to balance the charge, and let us say that is AXZ. So if we balance the equation, then we will get 232 is equal to 24 plus 0 plus 8. So from this A comes out to be 208, and coming to the Z, we have 90 is equal to 2 minus 4 plus Z. So Z comes out to be okay, I think Z comes out to be 92. Oh, sorry, this will be 12. This will be 12. This will be 12. So 90 minus 8, that will be 82. So 82 and 208, that is option C. Now let us move to the next one, question number 35. Using a nuclear counter, the counter rate of the emitted particle from a radioactive source is measured. At t is equal to 0, it was 600 counts, 1600 counts, and t is equal to 8, it is 100 counts per second. The count rate observed as per count rate second, that t is equal to c. So we have to find out that what is the time count, what will be the count rate at t is equal to 6. So this is basically activity. So we can write that RT is equal to R mod e raised to power minus lambda t. So this will be 100 is equal to 1600 e raised to power minus of 8 lambda. From this, 1 by 16 is equal to e raised to power minus of 8 lambda. And from this, ln of 16 is basically equal to 8 lambda. Now we have to find out count rate at t is equal to 6. So for that, again using the same equation, that R at 6 will be equal to R node e raised to power minus 6 lambda. R node is 1600, and I will have value of lambda. So from this, lambda is ln 16 by 8. So e raised to power minus 6 into ln 16 by 8. Now what I can do, I can slightly modify this part. So let me do it separately. So here I have e raised to power minus 6 into ln 16, which I can write ln of 4 square divided by 8. So this will be e raised to power minus 6 into 2 into ln of 4 by 8. So that will be again 3, oh sorry, 4. That will cancel on 4, and that further cancel on minus 3, and this is on minus 2. So this is e raised to power minus 3 by 2 ln of 4. Now ln 4 can further written as 2 square, ln of 2 square. So this can be written as ln minus 3 by 2 into 2 into ln of 2. So again 2 gets cancelled. So here I have e raised to power minus 3 ln f 2, and this I can write further e raised to power minus ln 2 cube So that is basically e raised to power minus ln of 8. So that's how I can modify it. Now what I can do further, I can write it like e raised to power ln. This minus sign comes inside and it makes it 1 by 8. Now e and ln are cancelled and I have effectively 1 by 8 left. So now I can substitute it here, that 1600 into 1 by 8, that will be equal to 200. So option A is the right answer. So with this, let's move to the next one. A sample of radioactive material A has activity of 10 millicurie. Curie is also mentioned, has twice the number of nuclei as another sample of different radioactive material B, has activity of 20 millicurie. The correct choices for half-life of A and B then be respectively. So we have to find out their half-life. Now starting with the activity. Activity of A is 10 millicurie and activity of B is 20 millicurie. So basically we can say activity of B is basically twice the activity of A. That is the relation we are having here. Now we know activity is lambda times N. So lambda times Na will be equal to lambda A, lambda B into NB, because we are writing it for B, will be equal to twice the lambda A into Na. Now you have to keep in mind here that this Na and NB are the value of number of nuclei at that particular time, means they are changing and they follow this equation, that NB will be equal to NB node, that is the original number, into e raised to power minus lambda bt. But as we are doing this calculation at time t is equal to 0, means at the starting, so NB is equal to NB node. So now we have this relation, and also it is mentioned that A has the twice number of nuclei, means n of A is equal to twice the n of B. So if from this, if I calculate the ratio for lambda A by lambda B, so lambda A by lambda B will be equal to NB by twice of NA, and value of Na is again 2NB. So from this, lambda A by lambda B is equal to 1 by 4. Now we know that lambda is ln 2 by t half. So this ratio lambda A by lambda B will give us the t half for B divided by t half for A will be equal to 1 by 4. So now let us see the options. Okay, it is first mentioned for A. So for A it is mentioned 5 days and for B it is mentioned 10 days. So 10 by 5 will give us 1 by 2. That is not right. Now let us move to here. 40 by 10 will give us 4. That is not right. Now here in option C, 5 by 20 will give us 1 by 4. So C is right. And in the last option, we will have 10 by 20, that is half. So that is not also right. So option C is the right answer here. In the next one, at a given instant at t is equal to 0, two radioactive substances have equal activities. The ratio of their activities of their after time t itself decays with time as e raised to power minus 3t. If half-life of A is ln2, half-life of B, we have to find out. So at t is equal to 0, at t is equal to 0, activities are equal. So R of A at t is equal to 0 will be equal to R of B at t is equal to 0. So that will give us that lambda A into NA node, because at time t is equal to 0 we have original amount and no atoms are decayed, is equal to lambda B NB node. So this is the first relation we have. Now we have to find out ratio of activity after time e raised to power minus 3t. So after time t, the ratio can be written like this. that RB by RA will be equal to lambda A NA at time t divided by lambda B and B at time t. So that will be equal to lambda A and a node e raised to power minus lambda A t divided by lambda B and B node into e raised to power minus lambda pt. Now we know that lambda A and A node is equal to lambda B and B node, which means these terms gets cancelled. So this ratio comes out to be e raised to power minus lambda AT by e raised to power minus lambda BT. Now time is already mentioned and decay constant for A is ln2. Oh, sorry, ratio is mentioned, not not time is mentioned. Ratio of RB by RA after time t is e raised to power minus 3t. So this is e raised to power minus 3t. Now I can write it like this: e raised to power minus 3t is equal to e raised to power minus lambda A plus lambda B t. So if I equate, then I will get that minus 3t is equal to minus lambda A plus lambda B, or basically 3t is equal to lambda A minus lambda B. Now, half time of A is ln2. So half time of for A, we know that T half is basically ln2 by lambda. So for A, that is ln2 is equal to ln2 by lambda of A. So from this, lambda of A is equal to 1. And sorry, I forgot to cancel t here because t will get cancelled. So lambda A is 1. So from this, 3 is equal to lambda A, oh sorry, 1 minus lambda B. And from this I can write, sorry, I made a blunder. The blunder is that I was taking RB by RA. So it has to be NB. Here it will be lambda B, it will be lambda A, and it has to be lambda A. So it will be lambda B and lambda A here. So this will be lambda B, lambda A here, lambda B, lambda A. You can correct it yourself, and hopefully I think you have already noticed it. So let me make this correction. So here I will have B minus A. So 3 is equal to lambda B minus 1, and from this lambda B is 4. Now this is right. So if lambda B is 4, now I can calculate the half-life of B. So half-life of B will be ln2 by lambda B, that is 4. So option C is the right answer here. Now let us do one more question. So at some instant, a radioactive sample S1 having an activity of 5 microcurie has twice number of nuclei as another sample S2 which has an activity of 10 microcurie. Half-life of S1 and S2. Actually, we have we have already solved this type of question. This is similar to that one. So let's do it. So activity of S1. So R of S1 is equal to twice the number of which has activity. Oh, sorry. Here activity of S2 or S2 is equal to twice the activity of S1, as S2 has activity of 10 and S1 has activity of 5. So these are the ratios, and from this I can write that lambda A into n S2 is equal to, and that is S2 node. So sorry, lambda S2, and this will be twice lambda S1 and S1 node. So this is the relation basically. Now it is mentioned also that nuclei of S1 is the twice the number of sample S2. So NS1 node is equal to twice the NS2 node. So from this, I can write that NS2 node divided by NS1 node is equal to twice lambda S1 by lambda S2. Now this ratio, this is S1, sorry, this ratio will be half. So from this, lambda S1 by lambda S2 comes out to be 1 by 4, and we know that lambda is basically ln2 by t half. So from this I can write that t half for S2 divided by t half for S1 will give us a ratio of 1 by 4. And if I match that 20 by 10, that will be 2, so wrong. 20 by 5, that will be 4, that is wrong. 10 by 20, that is half, wrong. 5 by 20, that is 1 by 4. So option D is the right answer. So with this, I end this video here. Hopefully whatever we have covered till now is helpful to you. Again, if you have any doubts or suggestion, put them in comment section. I will like to resolve them. And find it useful, share it, subscribe to channel, make some donation. And with this, we will meet in next video.